Thanks, Marion. As Marion said, I'm Adrian Hickford from the Transportation Research Group here at Southampton. I'm also the DAFNI champion at Southampton. Part of that role is to try and help link the Southampton infrastructure research community with the DAFNI facility. That's one of the main reasons for hosting this event today. It made a lot of sense when we were organising this to make it a joint event with UKCRIC, as we've heard, there are lots of overlaps between DAFNI and UKCRIC, especially in relation to the people and the facilities we have here at Southampton. So the next 3 short presentations will focus on the work that we've been doing here in Southampton, which involves DAFNI. I'll be introducing the NISMOD Transport model, and then my colleagues Marcus Young and Simon Blaney will show further examples of firstly rail modelling using DAFNI, and then the other DAFNI facilities which we have here at Southampton. So I'm going to give a very brief overview of the transport model, which was developed here in Southampton in TRG, but which is currently being transferred onto DAFNI along with the other NISMOD infrastructure models. It's already been mentioned by William and Brian. NISMOD is the National Infrastructure Systems Model, which was developed as part of ITRC, the Infrastructure Transitions Research Consortium. And the transport model sits alongside other interrelated models for energy, water, waste and digital communications. I'm going to look back at some recent research using the transport model undertaken by the model developer, Milan Lovrich, by Simon Blaney, by myself and others. And then looking briefly at how some of that work is being used to test the new implementation of NISMOD and how some of the outputs from the transport model will look using DAFNI. The transport road model is the one that I'm most familiar with. It's based on the British road network, and it's got underlying data which mirrors the Department for Transport's counts and estimated flows on major routes. And there's an associated sort of underlying origin destination matrix, which is used to calculate and generate future route choices. The model is designed to assess the impact of a number of input variables, such as population change over time. It shows the population projections for a specific housing growth scenario in Hampshire compared with the ONS projections. This is some work that we're currently undertaking for Hampshire and Southern Transport. We could also look at, for instance, changes to the vehicle fleet in terms of fuel types or engine types, for example. So we can compare the differences between a slow version and a more rapid change towards electric vehicles. The model can also incorporate changes to the road network in terms of capacity enhancement or other interventions such as congestion charging zones. So for a given socio-demographic scenario, the model can predict a range of metrics, including travel times, energy use, vehicle kilometres and emissions. And these metrics are disaggregated in different ways by time of day, by road type and vehicle type. And the outputs are spatially disaggregated at the local authority district level. We also have models for railway station and airport demand. Marcus will be talking something about railway soon, but I'll be looking solely at the road model. So I want to give you a flavour of the model capabilities. So I want to look at a couple of projects which we were involved in the last 2 or 3 years that have featured outputs from the transport model. The Oxford-Cambridge ARC case study with ITRC, which has already been mentioned, and a project with England's Economic Heartland, or EEH. But for the ARC study, we wanted to demonstrate the capabilities of the whole of the NISMOD modelling suite. So we looked at the future impact of different population growth scenarios, which were based on the development of a significant number of new dwellings in the region, and the effect that that population growth has on infrastructure demand across multiple sectors: energy, transport, water, digital communications. We looked at 2 main scenarios of development: either expansion around existing built-up areas, or the development of new settlements within the region. And the graphic on the left there comes from work carried out by colleagues in Newcastle and Leeds, looking at the spatial options for these new developments, given particular attractors and constraints. We also wanted to consider how to overcome some of the mobility constraints in the region, particularly the east-west connectivity between Oxford and Cambridge, which is relatively poor compared to the north-south access. So we also considered the impact of a new expressway connecting Oxford and Milton Keynes and Cambridge, along with some improvements to the regional railway infrastructure. And one example is shown here in this graphic. Looking then at some of the outputs from the transport model for this study, this chart shows how emissions are likely to reduce over time. So even though population is increasing, we're assuming that there are more electric vehicles and vehicle efficiencies are improving, all of which contribute to the reduction in emissions. We can see the impact of population change in these graphics, which show CO2 emissions for 2050 in each of those population scenarios compared to 2015. You can see that the lighter green says that the CO2 emissions are much reduced compared to 2015, but there are still pockets of higher CO2 emissions concentrated in those darker areas where the new housing has been introduced. We next used the transport model in a study for England's Economic Heartland, which covers a similar region to the ARC, with some additional local authorities making it slightly larger. For this study, we only had to consider one growth scenario, which was based on the currently planned housing developments in the region extended to 2050. And you can see there's actually much more variation in 2050 for the EEH growth scenario on the left, compared with the ONS population projections on the right. So given this change in population, how do we meet the targets of net zero carbon transport emissions by 2050? So there are a number of different approaches we could consider. So we developed a small number of different pathways to reach this end goal. We've made one major assumption that, except for the business as usual pathway, all vehicles are zero emission vehicles by 2050. So we achieve the target. We're actually getting to that situation is going to be a real challenge. We're going to need some major changes in legislation, public attitudes and behaviour in future years. But while that's an overly optimistic set of pathways, this is what the EEH team wanted us to focus on. So as well as our baseline pathway, we have three different approaches to decarbonisation. There's a highly connected future, which changes the way the transport network is used through embedded technologies. There's a future in which the vehicle fleet undergoes rapid technological change, and there's a shift in behaviour towards more sustainable transport. And the transport model has got a limited set of levers that we can change to generate these pathways. So, for instance, in the behaviour shift pathway, we introduced a road pricing measure in all of the major built-up areas in the region. That discourages road travel and acts as a proxy for behaviour change. For the adapted fleet pathway, we can change the rate at which electric and autonomous vehicles introduced to the fleet so that it's more rapid than in other pathways. So pulling these different levers gives us different results for each of the pathways. Looking at some of the results then, and since we've assumed that all vehicles are electric by 2050, there are zero tailpipe emissions in 2050. But you can see that there's a more rapid, the more rapid technological advances in the adapted fleet pathway have got a much more noticeable effect in the short term. The impact of those technologies is also evident for electricity use, which rises dramatically in all the pathways. But again, those vehicle efficiencies for the adapted fleet pathway suggest that that may help to limit the demand on the energy system in the future. This graphic shows the average speeds in the road network by time of day. Those dips there showing the slower, more congested peak periods. Now, naturally, higher populations will generate more traffic, so we can expect that there'll be more congestion in 2050. But you can see there the effect that road pricing measures might have in the behaviour shift pathway, that yellow line slightly less bad than the others. Although it does look as though none of the pathways are particularly effective at tackling congestion. So that hopefully gives you an idea of some of the capabilities and some of the limitations of the transport model. Now, for these studies, we've been running the transport model locally using Southampton University's high-performance computing facility. But since NISMOD is currently in the process of being transferred onto DAFNI, it should hopefully make it easier to set up new model runs to work with different data sets and produce visualizations, which currently have to be done offline in Excel or Python. I just want to show you a couple of examples of how these visualizations will work once the model is up and running. These screenshots have come from Martin Robinson at Oxford University. He's working on developing these visualizations for NISMOD specifically. This output graphic actually is using the emissions data from the EEH study. I'm not going to go into the details of what's happening here, but this shows you the various options for generating a variety of visualizations from different types of data sources. Because most of the output data for NISMOD has a spatial element, we can use that to generate maps and other visualizations to help us tell the story about what the results actually mean. This here showing different speeds on the road network at a particular time of day. Hopefully you can see that having this kind of functionality is going to make it a lot easier to generate new charts or other types of outputs from new model runs. And while this is just one example from the transport model, I hope that with Beth and Tom's demonstrations earlier, we've given you a flavour of some of the potential applications for using DAFNI and how it might be applicable to your work. And there will be an opportunity to discuss that later, but now I want to hand over to Marcus, who will talk briefly through some of the rail-based work he's been involved in using DAFNI.